How many of you have, how many of you understand the idea of deep learning? Can I see a quick proper raise of hands? It's a very simple concept, by the way. It's not a complicated thing to understand to start with. How many people understand the idea of deep learning? How many of you have no idea what deep learning is? Good. So you are my audience today. So this discussion, again a very quick discussion that we'll have in the next 40 minutes is on deep learning. So we'll have it in two parts. One's a deep learning theory discussion where I need to tell you what exactly it is. That will take more time, where we'll start with a discussion on regression. Now I'll assume that you have some mathematical and statistical understanding from your undergraduate, and then we'll have a discussion on neural networks, which basically constitute a deep learning architecture. And then in the last few minutes I'll demonstrate a code which and I'll demonstrate a code based on the discussion that we have on deep learning for image recognition, image processing with and without GPU. So one will run on CPU, one will run on GPU, and I'll demonstrate how to write that code very quickly. Okay. So let's talk about the theory first. So these slides will happen very quickly. If you have a question, you have to raise hands. I'll be happy to answer that. So regression. Now all of us understand what regression means. So let's take an example here. We have a plot, a data of size of house versus the price of house. Okay. It's a very standard kind of an information that you need before you want to buy a house. That what does the price of a house depend on? Now this is a very simplified example. I mean, size of house is not the only feature that decides the price of the house, but let us assume that that's the only feature. So I plot, I take a lot of data from market and I plot them as these red crosses on the plot, where the x-axis is the size in feet squared and the y-axis is the price in thousands of dollars in this case. So what I'll do is I'll fit a straight line. That's called a linear regression. A best fit line that's fitting this data is called linear regression, and then based on this, now that's my first model. That's a machine learning model, in fact, fancily called nowadays. But many people will end up doing this and call it a machine learning algorithm, where now we have an algorithm that will predict the prices of houses given any size. You feed in the size, this black box will predict prices. In the black box, you may just be doing a linear regression. So that's what it is, right? I'm sure everybody understands linear regression, right? Now let's look at this slide, which is got a lot of data in it, but just follow with the cursor. Let's change the color. Right. So just follow the laser pointer, don't try to read everything. So we have the size in the data and the price. So this data is called a training data or a training set or data set. So training set is basically that you use to train the model. Okay. So if you want to fit a straight line, the data that the model will see to fit a straight line through it. So this is called training set. And so you want to have a model which predicts the prices. So prices are an output called a target variable, and the input to the model is going to be the size in feet squared. So that size is an input or a feature of the model. So these are called feature variables, and the output is called a target variable. Okay, I will be using this terminology, so I am telling that. So output or target is what you want to predict, and input or feature is what you want to predict as a function of. And this process is called a supervised learning algorithm, because you know about the target. There are situations where you don't even know what the target is, but we will not discuss that. Supervised learning is situation where you know the outcome for certain sets, and then you want to predict the outcome for a new feature. So using this information, I want to develop a model that predicts the prices of houses of a given size of which does not fall in the data. And this x comma y will be a single example, and typically we will be using this indices as superscripts I, that stands for the ith example. So in this case we have a total of 48 data points, 48 red crosses. Okay, so ith data point can be denoted by xi comma yi. Well, so what happens? You have a training set, you decide on a learning algorithm. In this case I say linear regression. You develop this algorithm, basically a function. You put in the x values for new x is unknown, and it predicts some y hat. So a feature is an input to a model, and you have a prediction from that model. Well, for linear regression, what is the equation? We know that for a straight line, it's wx plus b, where w is the slope and b is the intercept. I'm sure everybody understands that, right? So y or f is equal to wx plus b in this case. So w and b are, so the input for this is x. Now again, this is terminology that we'll be using. So x is the input to the model, and w and x are called parameters of the model. So what happens in a model is you train the model to decide what are the good parameters or optimized parameters. So in this case, I want to fit a straight line with an optimum value of w and b. So w and b are parameters of the model, input is x and output is y hat. So we keep y, the actual y for the data, and y hat for what the model predicts. Now since it's a straight line fit, it will happen that what you predict, so let's say you fit in this blue straight line. So for this xi data point that you had, your data had this red cross, but your model predicts this this y hat. So there is a difference between your y hat and the actual y that was provided. So this is the error. Okay. So the way it works is you decide on some cost function, basically a function that you want to minimize, and the function will then be minimized, and for the condition for the minimum cost that you will have some parameters w and b, which are your final or optimum values of w and b. So in this case we use this. So how there are different ways to quantify error. The easiest way is to find the difference between these two, but just the difference is not good enough, because sometimes the red cross can fall above the blue line, sometimes below the blue line. Now they may cancel each other out if I add them, the two differences from different points. So what we do is we take a mod, or sometimes we take a squared. So in this case we are taking a square. So the difference between the prediction and the actual squared is called a loss function. Again, as I said, if you want to talk, you can talk outside if anybody is talking inside the class. So the difference squared is called the loss function, and loss is only for one data point. If you have many data points, then you add all the losses together, that's called total cost. And the aim of any a deep learning algorithm or machine learning algorithm is to minimize this cost function. And for the minimum condition, whatever parameters you get are the optimized parameters for the final optimized model. Any questions? Let's have a look. How does this J look? So J, let me show you this directly. So we have these red crosses, which are the data, and we have this, well, how do you start? Let's say we start with some arbitrary value of w and b. So that's an arbitrary line. So let's say we chose some initial w and b using a random generator function. Okay. So that created this blue line, hypothetically speaking. Well, that's a really bad slope. The data is going up and the slope is negative in this case, but that's a random w that you chose, so that resulted in this blue line. You can calculate the cost for that. Let's go back. How do you calculate that? Well, I put the blue line, I take the differences, put them here, add the squares of them, and divide by 1 by 2m, where m are the number of training examples. I get the total cost. So I do that. I get some value of cost, which is this blue cross, which has some value 77237. Then what I do is I have some algorithm that allows me to reduce the cost. So I run that algorithm. That algorithm is called a gradient descent algorithm. Many of you may have heard of it. It's like you're standing, let's say you're standing here on a mountain, and your aim is to go at this global minimum. How do you do that? Well, you just fall down. Gravity will automatically take you to this bottommost point. Okay. Another way is you find out what's the slope. If I have to quickly go to the bottom, I find that direction which is the steepest downhill, and that many of you may know is called the grad of the function phi. In this case the function is j. So what we do is we calculate that direction and we move in that direction. So we take small steps, and as we take small steps we finally go from this blue line all the way to the yellow line. And yellow line seems to be a good fit. and you can see yellow line is at the center of this contour, which is basically at the bottom of the pit of the cost function. So that means it's near the minimum cost. So we have reached the global, or the well, in this case we should say local minimum, but in this particular case there is only one minimum and the cost is small. So we take multiple steps. So here we have plotted j only as a function of w. Let us say b is fixed. So you can see it's and this is a parabolic function. You can see it's if you put in this y as wx plus b and you take a square, you get w squared. So that's a quadratic function. So that will look like this. Okay, in one variable. In two variables, it looks like parabola. Well, paraboloid. So our aim is to go at the center. So we use this algorithm called gradient descent algorithm. So the outline is you start with some j with some guessed values of w and b. Your aim is to minimize this cost function. So you start with some w, you keep changing w and b to reduce the value of j until you settle at or near the minimum. So there is a way to check if the change in the value of cost function with some step is very small, that would typically mean that you are near the bottom of the pit. Now this is for a situation where you have a univariate regression, but if you have multiple variables x1, x2, x3, so that becomes a multiple regression, right. So we are talking about this one dimensional situation where the prices of the house are only a function of the size, but it could be also be a function of the number of rooms, it could be a function of the number of floors, it could be a function of the age of the house, how old is it. So you have multiple input features and I still want a linear regression. So the function, it will look like w1 times x1 plus w2 times x2 plus w3 times x3 plus w4 times x4 plus b is equal to f. So that is still a linear regression in multiple variables. So there's so the algorithm works well in all cases. So how does the algorithm work? Well, you start with some w and b and you say that my new value of w is the old value of w minus something, and that minus is some alpha, which is some parameter, times partial derivative of j with respect to w. So this partial derivative is coming actually from the grad of j, which has two components in this 2D situation. One is del j by del w and the other is del j by del b. So this typically is a full semester course. I am doing that in 1 hour. So this is bound to be quick, but the idea here is that there should be a way to reduce or reach an optimum point where the cost is minimized. Well, multiple linear regression. So that's where your f is. You have multiple input features. That's more practical situation that you have. So it could be size, number of bedrooms, floors, years, and so on. So then you have an associated values of the weights w1, w2, w3, w4. So aim now is to find the optimum values of the weights 1, 2, 3, 4 and also b. So you have to, your outcome of this exercise is going to be 5 parameters to be optimized. So the more number of input features you have, the more number of parameters you have to optimize, the expensive it becomes computationally. So your f would be evaluated using w1x1 plus w2x2 and so on plus b. One idea here is called vectorization. So what you do is, rather than saying writing like this or in a loop, you say that I'll simply write my f as of w vector, which is a set of all w's written like this, dotted with an x vector, which is like this, plus b. Okay. So this is what I am showing here. I will not discuss the other parts of the slide. It's called vectorization. So this is readily implementable on the GPUs. GPUs can figure out vectorized situations. So try to write your code in such a way so that you are not using loops if you can use vectorized implementations, where basically we are saying w dot x. So if you understand linear algebra, you will actually be more comfortable with this rather than writing loops. You just use a dot np dot dot function that we already have discussed in this course in the beginning of the lectures. So let's summarize this process. Now we know how to train a model. How do we train a model? We have some parameters that we want to predict. We have parameters w1 to wn and a b. The model is looks like this. So model equation is basically saying that the f, which is the price of the house, is evaluated. If you give me a feature, some features x, I can tell you what the estimated price of the house is using this formula. But to start with, I do not know. I have some training data. You have given me some house prices as a function of some features for the last 10 years. So I would want to first find out the optimized values of this parameter so that I can fit a straight line or a straight plane in a hyperplane in a n-dimensional feature set. So what I'll do is I'll start with some guesses for all w's and b, and then I'll use this algorithm repeatedly many times, because remember, you have to start from some arbitrary point on that mountain, let's say here, and then you have to gradually take steps and go all the way to bottom. So you have to do these, the steps have to be small, because if you take a large step you may end up going too far away. So steps have to be small and many. So we repeatedly keep on improving our estimates of w's and b for some amount of steps, and there is a way to figure out if this number of steps are enough or not, and eventually I hope that I will reach at the bottom of the pit, which is basically your optimized values of weights and the bias b. And then once you know these weights and b, well, the model is ready. You give me a new values of feature set, I can predict the house prices. That is what modeling is. With some information of a large data set, I build a model and then I can use the model to predict some new information. Is this clear till now? So there are some more ideas that I do not want to touch upon. It's called feature scaling, hyperparameters, how do you decide the value of alpha, for example, and so on, and regularization. So these things you will learn in a proper deep learning course, but this was the idea of linear regression. Now another related idea is, well, there are classification problems. Well, a problem typically that I am showing you here is that you have some data, and based on that patient data you want to figure out whether the patient has the tumor which is cancerous or non-cancerous. The tumors can be of two types, malignant or benign, cancerous or non-cancerous. So how do I figure that out? In this case I do not want to figure out some value, I just want to figure out yes or no. So for this we use something called logistic regression. So earlier what we did was we calculated w dot x plus b, that gave us some, that will typically give us some value which can be anything. So we put it into this function which is called a sigmoid function. Sigmoid function is 1 upon 1 plus e to the power of minus z. So if you put in this w dot x plus b, which is between minus infinity and plus infinity, this actually ends up mapping this result w dot x between 0 and 1. You can check, if you have a very large value here, let us say infinity, then e to the power minus infinity is 0, so this becomes 1 upon 1, which is 1. If this is minus infinity, so that becomes e to the power of infinity, which is extremely large, 1 upon extremely large value is tending to 0. So this function ranges between 0 and 1, so that is called a sigmoid function. You may have seen this in your mathematics or some course if you have taken some theoretical courses. So now this is a good function, because whatever regression I do, whatever w's and b I calculate, I can calculate them in such a way so that when I put that into this function to calculate f, that f will vary between 0 and 1. So what I will get is, the interpretation of this f that I will get is a probability. So your actual data will be either 0 or a 1, it cannot be a, I mean either you tell the data set that this target is cancerous or non-cancerous, but your model will predict something which is between 0 and 1, then you can decide that if my value of f is predicted to be larger than 0.5, I call it cancerous. If it is less than 0.5, I call it non-cancerous. That depends on how you want to, I mean how safe and so on, but let us say for now that this is how you will decide, but you will get as an output of the prediction as some number between 0 and 1. So that is a probability. So this is called logistic regression as opposed to a linear regression. Well, the cost is different in this case. The cost is a sum, remember cost is always a sum of losses. So loss is for one data point and cost is a combination of all the losses. So it can happen that some of the data points are very close to your model, that is good, but some are very far away from the model. So you want to add up all and overall minimize your losses so that you get a best fit. because if it fits some data really well and some data really bad, that's not a good fit. A good fit is if it fits the whole data in an average in a good way. So that's a global optimized situation. So you calculate losses in a different way in logistic regression. We say that for a situation where the value of y is 1, let us say cancerous is 1, then the loss is calculated as minus log of the value of f of x. F of x is what you calculated from your model. And then if it's 0, that is non-cancerous, then it's minus log of 1 minus f of x. So this is typically in models called binary cross entropy. So this is a standard logistic. I mean, there's a lot of discussion that you can read on this choice of cost function, because it results in a convex cost function. Convex means that it has a nice global pit at the bottom that you can, so that function looks very nice when you plot it. Right, so that's the end of regression. Is it clear? I think that's one of the quickest discussion on regression in my history that I've heard. Right, so why are we discussing this neural networks deep learning now? Because now we have a lot of data and we also have a lot of compute power. So with this collection of lots of data and lots of compute power, we can actually build very good models. So that's the reason we're talking about these neural networks, in fact large neural networks. So what is a neural network? Those who have never heard of it, well, that's lots of regressions collected together. So if you understand one regression, it's many regressions. So this is typically, you may have seen this layers of neural networks. So this one circle is called one neuron. Okay, it's nothing to do with your brain, but that's how the ideas originated. So one circle is called one neuron, and one neuron is one linear regression or one logistic regression. So what does a regression do? It takes some input data x1, x2, x3, x4, and it builds a model f which is w1 x1 plus w2 x2 plus w3 x3 plus w4 x4 plus b, and it results in one output which is the value. That's what one neuron does. Another does the same thing but with different weights, let's say. Then you have a third one. Okay, so this okay, so let's say you have these you have this x vector. So what that is, that vector has components x1, x2, x3 and x4 for our example that we took. So this one neuron is going to take input from these 4 vectors and give in some value y. Then the other neuron, let's say the third one, again is going to take these inputs and build another, let's say y3, this is y1. So it's basically a complex system. You have lots of simple things happening in the system. So if you understand linear regression, it's lots of these. Okay, and then you have layers. So what are the layers? What do the layers signify? Well, so what I am saying is that the output of one neuron is the output of one linear regression. That's one number. Remember, output of a linear regression is just one y. So that's one number. Let's call it A1. Output of another neuron is another A1, A2. This is A3. So the output of the first layer is 3 numbers. So it's like you have some new inputs. A1, A2, A3 are similar to x1, x2, x3, x4. So now when I talk about, let's say this neuron, then this takes inputs from these 3 values. So A1, A2 and A3 are the inputs to this neuron, and this will now predict some new value, let's say A4. Okay, and then this will be A5, and finally the output neuron will take inputs from A4 and A5 and predict some A6. Ultimately, you will have one number out of it, which can be either more than 0.5 or less than 0.5, then you can say it's cancerous or non-cancerous. Is the idea clear? Any questions? That's what deep learning is. Well, it's a lot more than that, but these are the ideas of deep learning. And then you combine these in a dense way or some way to get different architecture. This is architecture. How many layers, how many neurons plus per layers, this defines an architecture, how the connectivity is between neurons. So here I said that all the inputs are connected to neurons. So that's called a dense arrangement of neurons in an architecture. So that's called a dense layering. So this is exactly what I have discussed. We are zooming into this particular layer which has 3 neurons. Let's look at the first one, the first neuron. So here we say that the output of the first neuron, which we call A1, is some w dot x plus b, and so we are doing a logistic regression. So this w dot x plus b is not, if it was linear regression, that's what we will do, but here we are also doing a g of that, and g is this sigmoid function. So this is a logistic regression. So we calculate this a as 1 upon 1 plus e to the power of minus w dot x plus b. So that gives the first output of the first neuron. Similarly, you have the output of the second neuron, similarly the third neuron, A1, A2, A3. So these are called activations, terminology. Okay, output of a neuron is called an activation. Clear? So typically you will see that it will be some number. Next is the output neuron of the layer which has only one neuron. So well, the output layer takes in the activation vector from the first layer, which is basically 3 numbers, and feeds into this. So it calculates this A1 of the second layer. So the superscript is basically for the layer number and subscript is for the neuron number in the layer. So A superscript 2 is for the second layer and subscript 1 is basically for the, it is only a one neuron, so there is only A subscript 1 here. So that's G of the sigmoid of W1 dot A1 plus B, and that's your final output. So that's just one scalar value. So if the scalar value is greater than 0.5, the cancer is the tumor is cancerous. If it's less than 0.5, the tumor is benign. Well, this was a simple situation. You will have lots of these. Moving on. So if I tell you, so each neuron has lots of weights. So it has a weight. It has a weight and a b value, right? This also has. So let's say this is. I now need a notation. So I call this W superscript 1. That's for layer 1, neuron 1. So the weights for this will be W superscript 1, neuron 2. Similarly, I will have W superscript 1, neuron 25, because I have 25 neurons in the or units in the first layer. So now you see, now how many weights do I have? Well, that depends on what's the dimension of this x vector. Let's say x was a total of 400 features. So this will be an array of length 400. Similarly, all of them will be 400. So you can see there are lots of parameters now, and this is just one layer. Another layer has more weights and b's, and so on and so forth. So you have to train a lot of parameters. So you need a lot of computing power, and this is where our GPUs will help us. Well, how does it work? The same technique. You have lots of linear regression. Ultimately, your prediction will be just one value. You have the original data, right? So the data tells you that this is a y and this is a y hat that is predicted using this dense configuration, but ultimately it is this one, you feed in some x values, you get some output. So we take the difference, or we have some way to calculate the loss, and then we add all the losses to get the cost function. So once you have a cost function, you can apply the same technique of gradient descent in steps, small steps, until until you reach the global minimum, and that will be the best combination of these parameters W's and B. So now we will discuss about TensorFlow, because TensorFlow is so in deep learning you do not write codes from scratch. You can do that for an exercise, but we do not typically do that. So there are two major frameworks that are popular. One is called TensorFlow. What is the other one? PyTorch. So TensorFlow is by Google, DeepMind, Google, and PyTorch is by Facebook or Meta. So these are the two major frameworks available. Our discussion will be using TensorFlow. PyTorch, again you can have a look at Google for codes. Well, so we said we had different number of layers. So we had this, in this case we had 3 layers. So all I have to tell to the framework is I need 3 layers in this case, layer 1, 2, 3, and I have to tell how many units are there, how many neurons are there per layer. So that is what we specify. We say layer 1 is equal to, now again it is a dense architecture. So dense means that all the inputs will be used. 3 units, what is the function? Sigmoid. So you can use a linear function as well. So that will be linear regression. So I told you neural network or neural networks are basically each neuron is doing regression. Now some of them you can make them do logistic regression, some of them can be made to do linear regression, and there are other kinds of activation functions as well. So here we are saying all of them are logistic kind of, basically they take in some values and they predict some number between 0 and 1. So that is a sigmoid function ultimately that gets mapped to the w dot x plus b. So we have to tell these information, units and activation function. So we develop these 3 objects, layer 1, well in this case we have only 2 layers, layer 1 and layer 2. So layer 1 and layer 2, layer 2 has 1 unit, it is an output layer with sigmoid activation function. Then we say the model, then we say the model is a sequential model with first layer 1 and then layer 2. So that is how you define an architecture. Then you have to define some x and y. So x and y, sometimes you will take it from some data set. Here they are defining, but let's not worry about, let's say x and y are available, that is coming from some data. So first you say model.compile, you compile the model, I will talk about it, then you say model.fit. So now once model.fit is done, you have got the optimized values of w's and b's. So once you have the model parameters available, all you have to do is you have to predict. So now you give me new features, I will tell you what the target is. That is what you expect the model to do, right? So I told you this is a more, well that was more of a pseudo code, this looks more like a code. So first you import TensorFlow, then you import sequential, you have to import dense, all these classes have to be imported, and then you also have to, I told you that you need this compile function. Basically to compile function you have to specify something called the, what kind of loss function you want to use. So in this case, since we have all sigmoid activation functions, I want to use a loss function which was this minus log kind of loss function, that is called binary cross entropy, fancy name for that function, minus log of f of x, or 1 minus of 1 minus log of 1 minus f of x. Okay. So this is basically telling what sort of loss function you want to use, and then you fit. Now I told you have to take lots of steps, you can't go in one step, you have to take those minute steps. So each step in deep learning lingo is called an epoch. Okay. So we are using 100 epochs, means we are taking 100 steps to reach that final bottom of the pit, which is to get the optimized value. Now 100 may or may not be enough, more number of steps means closer to the optimum. That basically decides what sort of computing power you have. Do you get some idea of deep learning? So activation functions are different type. You can have a sigmoid type, you can have a linear type, you can also have a ReLU type. ReLU type is called a rectified linear unit. So this is linear. ReLU is for negative values of x, it's 0. For positive values of x, it's the same as linear. So rectified, from those from electrical engineering background will understand what rectified means. So basically you clip it to 0 for negative values of x, positive it's. Now there is a lot of discussion that you can read about why these are good or bad. So there are different kinds of activation functions available. Many people end up using lots of ReLU functions. They have seen that they are really good, and at the end they use a sigmoid function if needed. Right, so let's jump into this example. So what we are using for our discussion today is called an MNIST database. That's a collection of handwritten images of data. That's a standardized data. Many people use that to test their algorithm. There are some standard problems or data sets that's been shared. So if your model does good on those standard data sets, you can then define how good, quantify how good your model is as compared to other standard models. So this is a data set of, I'll show you the pictures of some images of numbers from 0 to 9 written by people with their pencils. So you have 1, sometimes the 1 is written like this, sometimes the 0 is like this, sometimes the 0 is like this, sometimes it's like this. So there are lots of pictures, and for those pictures we have people have sit and said that okay, this is a 0, this is a 1, this is a 1, this is a 0, this is a 0, this is a 0. So you have images as input and the target is some number 0 or 1. Okay, is that clear? But the input has to be a vector x. Well, that's easy. What is an image? An image is pixels, right? So let's say I have one image where I have a 1 written like this. So an image is nothing but pixels, and a pixel can be black or white. Let's say it's a thresholded image, a 0 or a 1. So 0 means no light, 1 means light. So regions where you have a 1, you have some text, that will become a 1. Region where you have nothing, these will all be zeros. So basically if my pixels is 20 by 20 pixels, I have a total of 400 numbers going from 0 to 1, ranging between 0 and 1. Well, actually being 0 or 1, there cannot be anything between that. So my x is a total of 400 pixel values, right? So I can actually flatten that into a vector x of size 400, size 400 by 1, which has the numbers 0, 0, 0, 1, 1, 0, 1, whatever. So that will result in, I can actually map this 400 by 1 vector to an image or vice versa. So if you give me an image 20 by 20 pixels, I can convert that to this x vector, and then I can use this as an input to my neural network model. Right. So first we have to install things. So what I have done is I have installed it in a Conda environment. I need to install CUDA toolkit and CUDA, and I also need to install TensorFlow, which I'll need to import in my code. These instructions are available on TensorFlow website. You can have a look. So I will open the Anaconda terminal. It's like pip, okay? It's like it's like virtual environment. So I'm just having a look at what's the environment name. I have these environments available. The one I created was called Keras env. So I'll say Conda activate Keras env. So that activates the environment. Now I can open Jupyter notebook. So this is the neural network that we are going to use. It has 3 layers. The first layer has 25 units, second layer has 15 units, and the third one has just 1 unit. The input is going to be an image which is like this, which is basically an x vector of size 400 rows and 1 column. Okay. So what I am doing here is, I hope the people at the back can read this. Can you read at the back? So first I'll import time because I want to have a tick and a talk to see how fast my code is running. Now I'm importing some things like NumPy, TensorFlow, sequential dense, some plotting things and some other stuff that I have written in other files. Don't worry about that for now. So this is where if TensorFlow is installed, so it's run, so that's done. Now I have to load the data set. I have kept the data set in the same folder in some files as numbers. So I have defined a load data function in some other file which was autils. So this has imported the data now. You want to check x of 0, remember x is a collection of images. Each image has been flattened into 400 numbers. So if I print just the first image data, that will be a total of 400 numbers. In fact, the number is ranging between 0 and 1. It's not just 0 or 1. So the pixels are ranging between 0 and 1. That's what I think is happening here. Okay. I can also print the value of y. So y, the target is either 0 or a 1. Okay. I can show you shapes, sizes. So x has a total of 1000 examples, 1000 images. Each image has a size of 400 pixels, and the target is just 1000 by 1 because each image corresponds to one target, a 0 or a 1. Now this is where we convert these numbers x to images, because it has taken the data x that were just numbers and converted that to images, and it's also shown the target on the top. So this is the data that I just downloaded as numbers. So you can see that the 1 sometimes look like this, sometimes this, 0 sometimes looks like this, and so on. So then people have sit and put targets here. So this is my input data x and y. Now we have this model where we say that the sequential model has 3 layers. The first layer is a dense layer of 25 neurons with a sigmoid function. Second one has 15 neurons with a sigmoid function. The third one has 1 neuron with a sigmoid function, and you also have an input x to start with. We run it and hopefully it runs. This is where things can fail if your model is large and your memory of GPU is small. I have a good GPU on my machine, and then I can print the summary of the model. So this model.summary will tell you at any time that you have these layers and this is, and the parameters. So the number of weights you have, or the weights plus b. So you have 10,000 parameters in first layer, second one has 390 parameters, this last one has 16 parameters. So you have a total of 10,431 parameters and you have to train all of them. It's a lot of training. You have to train 10,000 parameters, you have to find 10,000 weights and b's. So you basically have to optimize to find the optimum values of these functions. Remember, one linear regression was just one w and one b. You have 10,000 plus parameters to train here. This is just some test, don't worry about this. These are just again printing some things. This is compile. So this is model.compile. You provide the loss function and then you have a model.fit for 100 epochs. Well, it has worked for 100 epochs. Now you say prediction is equal to model.predict. So this is basically predicting for one particular case. Now you say if the prediction is larger than 0.5, you say it's 1, if less then it's 0. Now what we will do is, for all the cases we will predict. So the result will be the picture and the label, the target that was given to it, and this second target, second y hat is basically what you predicted. Our prediction is really good. I mean, it's basically perfect, right? There is no discrepancy. Now those who understand this, they will say that this is cheating. You train the model on the same data, you test it on the same data, that's not allowed. But this discussion is not about the idea of deep learning, it's about how to do it. You can split the data into training and test. You train on some part and test on the other part, that's okay. And this finally is giving the final time. Well, this is not good because I waited a lot of time. So what I will do now is I will say restart and clear output. So that will restart my kernel, clear all the output, and now I will run all. So now it will run everything at one go, and finally when I get the output, that should tell me how fast my code ran to do all this exercise. Now this is all happening on the GPU. I can actually show you. So GPU usage is increasing. Okay, so that means that this is happening on my GPU card. There are different commands in the terminal you can use to figure out how much is the GPU being used. Well, actually GPU is also being used for display here. When I ran it at home, I was only using it for running the code, but that's okay. I already know that it's using GPU. So it took 16.9 seconds. Now what I'll do is I'll uncomment some things on the top. So what this will do is it will force the code to go on the CPU. So let's clear the data and everything. And now I run all the cells. Now what do you think? Should it be faster than GPU or slower than GPU? 16.9 seconds for GPU. 10 seconds. Because my machine has better CPU than GPU, okay? It's not that amazing of a GPU like you have on Param Himalaya. Okay? So again, don't just jump into using GPUs. Just do this sort of scaling as well to see what is good and what is bad. Any questions?